Hi, everybody. Shalom lekulam. My name is Erez Cohen. I'm with Mellanox. I apologize for my voice. I lost my voice. It's not my normal voice, only for special occasions. I hope it will run out. It will work throughout the session, but I'll try to speak as clear as I can. I apologize. I think here in Israel, it's relatively well-known, the company that we are from, Mellanox. But for you that are not aware, Mellanox is an interconnect, a networking company, where we basically provide very high-end network solutions. We are a public company, about 16 years old, and we mostly sell into the very large clouds and Web 2 companies. You know, the public one we can speak are, you know, the Azures of the world and the Facebooks and so on. We are also very largely deployed in scientific research institutes where they do a lot of simulations, large simulations, Earth weather, cancers study, and genome, and so on. And the reason I'm saying all of this is that Mellanox focus is really on the high-end side of the interconnect. And we're trying to make the cloud, and specifically OpenStack, to be able to work in high speed, just like those research institutes, just like other very large organizations. This is our aim when we're doing OpenStack. So we're trying to take the networking of OpenStack and make it run much more faster, much more efficient. Basically provide you a network without the compromise of all the virtualization, but still keep the flexibility and the agility of a cloud. That's our aim, basically, in OpenStack. Mellanox is operating mostly in Neutron, which is the networking section of OpenStack. Cinder, which is the storage. Nova, obviously, which is important for both, and Ironic, which is the bare metal provisioning. We're also working on other projects like Fuel, which is the orchestration. And I could talk quite a lot of things we're doing. As you can see, we are pushing quite a lot of work upstream. But what I want to focus on this very short time we have here is something a little bit more innovative, something that is a little bit looking forward ahead. And this is, how do we accelerate the in-host networking? How do we accelerate, for example, OVS? So with this, just a quick overview of what we'll cover. We'll talk a little bit about the challenges with OVS in OpenStack. We'll talk about the approach that we are driving called ASAP Square. I'll talk about it, and then I'll show you some initial performance results. So let's start with the challenges. So OVS, for those of you that are not familiar, is a virtual switch. It's a switch that runs inside the host, inside the server, typically in the hypervisor, and provides connectivity between the virtual machines themselves and the outside. As time goes by, there are more and more capability going into this virtual switch. It becomes a virtual router. There's talks to pull in firewalling capabilities and a lot of other networking needs. Out of the different solutions, OVS is the most common virtual switch in OpenStack. What you see here is from a study, OpenStack study, where they list all the different virtual switches. And OpenStack is deployed in over 40% of all the cloud deployment in the world. So it's very popular, and the reason it's popular is because it's very advanced. It is a flow-based switch, meaning it is able to switch not per destination MAC only, but also according to a specific flow. So we can address every flow of the network independently. So everybody is happy, and a lot of people deploy it, but there is some downside to it. And the downside is mostly performance. What we're seeing is that OVS, because it's running in software and running on the general CPU, is a limiting factor for the performance and the efficiency of the cloud. It runs slowly, and as a result, it drops packets, which is not very good, especially for telco guys where they need all the packets. And in addition, it eats up a lot of the CPU that we have on the server. Similar to OpenStack, there's a consortium called OPNFV. It's an open source consortium, very kind of adjacent to OpenStack. And the first summit was last year in November in the Bay Area in California. There was a panel of all the large CTOs of the operators, the big operators of the telco, the AT&Ts and the Orange and so on. And they are all agreed that the number one limiting factor for NFV today is the performance, and more specifically, the packet per second that they can get into the VNF, into the virtual function, into the load balancer, or into the whatever application that runs there. They're saying that they get today between 1/10 to 1/100th of the actual performance they need. And the impact is severe. It means that they'll need 10x to 100x more hardware to be able to carry the same workload. And obviously, this is a no-go for them. It's a no-starter. NFV will not work if you need 100 times more hardware. The power, the size, the cost is just not working. So what we would like to do is to show how can we solve these solutions. There are, in high level, two main directions. There's a lot of variance into that, but in general, there are two very distinct solutions. One of them is here, what you can see on the right, is para-virtualized. There's a lot of squares here. But basically, what it means that the virtual machine network connects to the hypervisor. It connects to the hypervisor, and then from there to the virtual switch. It is very flexible. It's great for control, because then in software, I can control the OVS and then implement SDN, and everything is portable and so on. And this is really the main use case in the industry today. On the other hand, there is the path of SRIOV, or single root I/O virtualization. This name came up several times here today. But basically what SRIOV means is that the virtual machine has direct access to the NIC hardware. This way we kind of bypass all the heavy lifting of the hypervisor and provide bare metal performance. But the downside is that we kind of lose the flexibility. We kind of lose the SDN nature of the system. And from here, there's other variants, right? There's DPDK that people are talking to accelerate. DPDK is a framework to accelerate networking. But what DPDK does is really just moving the problem from one hand to another. We're not against DPDK. On the contrary, we have the best DPDK performance in the industry today. But what DPDK does is just moving the problem from performance to CPU. So you're paying up in CPU, or you're unloading the problem on the CPU, and basically you're losing just cores. And this is the most expensive resource on your server today. So what we're looking to do, or asking ourselves, is what can we do to enjoy both worlds, right? The configuration and the flexibility and the SDN nature on one hand, but on the other hand, we want to have the performance as well. So with this, I'll move to the next part, which is the overview about ASAP Square, or accelerated switch and packet processing. So basically what we have done in very high level is we did מה שעשינו ב-48. You know, for those of you that, we looked back and say, okay, how do we solve this problem? And basically what we did, we went back and we separated the control plane and the data plane. We said, it doesn't make sense to run data plane of 10 gig, 40 gig, 50 gig, 100 gig. Today, Mellanox have an end-to-end 100 gig, 200 gig coming very, very soon. The telco guys, all of them, this is where they're going. So it doesn't really make sense to run it on more and more CPU. CPU doesn't scale to that level. We need real hardware. But on the other hand, we want the control. So let's run the control where the control needs to run, in slow path. But let's move the hardware to do the heavy lifting. Let's move the hardware to take care of the packet processing. And this is, in very high level, what we're doing. So accelerated switch and packet processing, ASAP Square, is an umbrella of technologies that we will kind of give you a glimpse right now too. The basis is that we use the NIC hardware capability. Mellanox NICs and other in the industry have an embedded switch inside the NIC. So the NIC today is much more smarter than the NICs that you know. It has an embedded switch. It's a flow-based switch, very advanced and a lot of capabilities in a ASIC. It's not running on a CPU or embedded CPU or an FPGA. It's just in the common NIC that we ship in hundreds of thousands a quarter. We have a switch inside that runs in ASIC. This switch is a flow-based switch. There's tables of flows and actions, and those tables are fully configurable in software. They're very scalable. They can hold hundreds of thousands and millions of flows, so it's very scalable. The NIC has a sophisticated matching or classification engines in hardware. So the NIC can do in hardware classification for the packets in 0 CPU and very quickly. And it's a very flexible classification engine. And based on the classification, we can do a lot of different actions. So we can do, for example, steering, forwarding, and so on. We can do drop and allow to implement ACLs. We can do hardware encapsulation and decapsulation for overlay network like VXLAN and other things. This ASAP Square, or this accelerated switch and packet processing, is broken into two different subgroups. The ASAP Square Direct, which is basically offload the full data path of the virtual switch. We're using SRIOV and basically keeping the network management in OVS and reflecting the rules. I'll go into that in more details. This is what we call the full virtual switch offload. And ASAP Flex, which is basically ability to pick and choose what elements of the offload to do, but still maintain this para-virtualized notion. To understand the full offload, let's just review quickly how OVS Open vSwitch work. In very quickly, it has two parts. It has a kernel module and a user space daemon. Packet hit first the kernel space daemon. The kernel space daemon is basically a set of tables similar to OpenFlow, if you like. The kernel will do classification in software, and then it will define what is the flow of this packet. And if there is an action associated with that flow, it will execute it. If there is no action associated with that flow, meaning that this is the first time the kernel see this flow, the packet will be forwarded to the user space. This is the slow path. And the user space will need to decide what to do with this packet. It will console the SDN or will do learning, whatever, it doesn't really matter right now. But eventually it will decide what to do with this path. And once it did, it will program the kernel to handle following packets. So the first packet is kind of slow path, and then the following packets are fast path. What Mellanox did, or is doing really, is using the same concept, but enlarging it or extending it so that we add another layer. So the first two layers up there you saw in the previous slide, and then the next layer is we're layering the embedded switch, the Mellanox hardware embedded switch. And the same concept like before works. So a first packet or a new flow will hit the NIC first. It will hit the NICs first because either it comes from the fabric, and then obviously it hit the NICs. But it can maybe also come from the VM, and the VM is connected with SRIOV. So again, it hit the NIC. It goes into our switch. We do classification in hardware. If there is a miss, we send the packet to the kernel. Same like before, the kernel will have a miss. The packet will go all the way to the user space. And then the user space will need to configure. This is the second part here. The configuration is policy-based. So there is a policy. Everybody can implement his own policy that can decide what to offload and what not to offload. And the user space can program both the kernel and the hardware with the same rule. Later on, every next packet of the same flow, when it hits the embedded switch, it will basically do the forwarding or anything else in hardware. And that's in 0 CPU and very, very fast. So latency is very, very fast and so on. In addition to that, we can do a lot of other actions like quality of service in hardware. People ask about jitter of quality of service and so on. So when you're doing that in hardware and the hardware is right, like what Mellanox knows how to do, then it works very nicely. One of the things that you may have thought about is, hold on, we said we're having SRIOV, so the VMs are bypassing the kernel and bypassing the hypervisor altogether. So how come the OVS, which is unaware of those virtual machines, even plan or program or even aware of those virtual machines? It doesn't know anything about those virtual machines. So for this, what we've done is we basically build a new entity in the Linux kernel. It is called NetDev Representer or Representer ports. What you can see here is a drawing where we have two virtual machines on the right-hand side, which are connected directly to OVS. This is para-virtualized machine. But then we have two SRIOV. So you see the links are connected directly to the NIC. But at the same time, OVS does have 4 ports. 2 of the ports are kind of dummy ports. They are not dummy completely, but they are representing the virtual machine that is connected with SRIOV. This way, the OVS can now program flows for that NIC, for those VMs, and can also inject packet or receive packet that belong to that VM for the slow path. So this is new elements in the Linux kernel that we are driving upstream these days. Now with this, basically, we have everything we need to enable the same environment as before, running over an accelerated system. So really what we have now is all the SDN controllers that use OVS, and there are many, can run intact without any changes, keep on the full flexibility and automation, but the underlying hardware will accelerate the data path itself. So we are maintaining all the capabilities of SDN. One word about OpenStack. So we are in an OpenStack summit, or OpenStack Day in Israel, sorry. We're also working to integrate that into OpenStack. For those of you that are a little bit in the details, there are 2 types of ports. There are direct and normal. The direct is SRIOV. And again, they are kind of oil and water. What we have done is we enabled the OVS layer 2 mechanism driver to bind into a direct, into an SRIOV interface. And by that, basically, we are providing the ability to provision an accelerated OVS into OpenStack. This is already, by the way, running, not yet upstream. It will be, but it's already running in testing. So, so this is, in very few minutes, just an overview. What I would like to do is to give you a quick status on where we are with this project, and then show you what's the outcome, what's the results, really. So in general, we are now working on a beta release of this that is already available. We're starting to push code upstream. We've been in NetDev, the Linux networking kind of conference, discussed this, got the community approval, basically, and we're now moving things upstream. Pretty soon, we believe by the end of this year, everything will be upstream and available for all of you. But for now, let me talk a little bit about the testing that we have done. What we did is we compared, in terms of performance, the highest performing solutions out there. We looked at message rate and we look at CPU load. We're running a 25 gig network with the highest performance. And our condition was really open source solution and free solution. We didn't look at unique hardware or anything else. We look at open source. I think this is what the people in the community is looking for. What the benchmark that we did is standard forwarding benchmark where we send and receive packets. It's called RFC 2544. This is the 2 systems that we compared. On the left-hand side, we have the OVS over DPDK. This is a version of OVS that is on steroid, so that basically OVS is bypassing the hypervisor kernel to get more performance. And also in the virtual machine level, we are running the benchmark over DPDK. So we're kind of trying to suck in as much performance as we can from the system. We're using an Exia packet generator to push packet in and out. On the other side, the VM is staying the same. We're using OVS-Offload, where basically we're reflecting the flows of OVS into the hardware, and then we're using SRIOV to push the traffic in, right? So the data flow is pretty simple. We are sending and receiving packets, so this is forwarding. In the left side, we're going through the hypervisor, and the right side, we're going through the SRIOV. So we are bypassing, but we continue. We're using the same open flow rules and everything else in OVS. This is the results that we see. They are very preliminary. They're looking at a single flow using VLANs. It is not VXLAN yet, because it's very new. But still, we can see very interesting results. So this is a zero packet loss. We don't want to see any packet loss. With OVS over DPDK, we've been able to get to close to 8 million packets per second, kind of aligned with other reports we saw in the industry, not of the open source OVS over DPDK, but the proprietary. We saw 9 million packets per second in some reports. But we had to dedicate 4 cores, 4 CPU cores, just to get to this number in the hypervisor. So out of the 20 cores I think we have in the system, about 4, which is a significant number, a very significant number, was spent just to run the hypervisor DPDK. When we run the OVS-Offload one, we get close to line rate, 33 million packets per second. To be honest, we would go even with the same number of packets per second, because what we were trying to do is just to provide you this without burning any CPU. But not only that, we do that with 0 CPU, we actually can push quite a lot more performance. Since I prepared this, we have some new update results. We're scaling out and doing VXLAN encapsulation in hardware. With about 2,000 rules or flows, we're getting to about 25 million packets per second with VXLAN encap decap compared to about 6 million in software. And the more we scale, the more the gap will grow, because we're not dependent in the CPU while all the other solutions are. So for conclusion, and this is my last slide, we're seeing quite impressive performance impact on that solution, both in terms of performance and CPU utilization. One of the things that I failed to mention is that we're going to open source, or we are open sourcing everything. All the application interfaces are standard. We'll use TC, traffic control, Linux interface, API, or DPDK. So basically, anyone can take advantage of this acceleration of OVS. And with that, I think I'm 1 minute ahead of time, and I'm opening for questions. Thank you very much. Good question. So the question was if this is available on all the Mellanox NICs. This feature available from ConnectX 4 and up. ConnectX 4 is the one that is currently shipping in volume. We're going to ship or actually tape out ConnectX 5 very soon. It will have even more enhancements on this. Yes?
What kind of configuration may be done on your features?
So this is, so the question was, what do we need to do on the switch side? So really, this is a host side element. It does got nothing to do with the switches. You can run it with Mellanox switches, which is obviously recommended by me. But you can run it with any switch. You don't have to do. One thing that we do look, if you think about what we're doing here is we are offloading the data path of the virtual switch. The same thing we can do also to the application, the VNF. itself that's running. We can offload the data path of the VNF also to the NIC. And a little bit in the future, we're actually going to offload the VNF data path into an element in the fabric. Then we'll be able to do some interesting thing inside the fabric itself. For example, utilizing network processors. We just acquired, I'm sure the Israeli team here heard, Mellanox acquired EasyChip, which is a very large Israeli company that's having network processors. And we're looking to use the same concept and the same kind of control plane, data plane separation, and be able to offload into the fabric, just like you're using today storage in a SAN configuration that is on the fabric, and you're just using it locally in your computer. The same way we would like to enable VNFs to offload some of their work into the fabric somewhere. But this is ahead of time. Any other questions? So the question is if it is different than replacing the OVS switch with a real physical switch. The question is, how do you do that? I mean, in the end of the day, you have virtual machines running on the server, and you need to provide switching to them. So how do you squeeze in a switch, a real switch? So just to repeat, the gentleman asked, basically the concept of OVS is to use a software switch rather than being tied up to a physical switch. The answer to this is basically we're not enforcing anything here. You can, if you hardware support it, you can accelerate. If not, you stay in the software level. It is completely backward compatible. There are many things today that you're offloading without even knowing. For example, just the most simple example. If you look at the networking stack in general, there is a checksum, right? Every packet has a checksum, and if you look at this in the Linux software stack, you would expect that the Linux will do that. But the fact is that if you do that in the host CPU, your performance will be very, very bad, even in 10 gig, without talking about virtualization, overlay, NSH, all this stuff. So very quickly, the industry understood that if you don't do some stuff in hardware, it'll just not work. So it enables the ability to offload when it is possible. It will not break if you don't have the capabilities. But the concept of offloading heavy lifting work to a NIC or to a switch was always there. We're just extending that. I think our time is up. We are here. If you have any questions, I'll be very happy to answer them. Thank you very much.